2.2 Equations of uniformly accelerated motion. 1. Deriving the equations of motion. For the car accelerates uniformly as represented by figure 2.2b, we may express its acceleration and displacement in the following ways. For acceleration, a equals v minus u over t, hence we have v equals u plus at. For displacement, which is the area under the vt graph, we have s equals half of the sum of u and v multiplied with time t. When we combine equation 1 and 2 and eliminate the final velocity v, then it gives s equals ut plus half at squared, which is equation 3. If we combine equation 1 and 2 and eliminate the time taken t, it gives 2as equals v squared minus u squared. These four equations apply to all uniformly accelerated motion as represented by figure 2.2b. 2. Applying the equations of motion. There are 5 variables, namely u, v, a, s, and t. While each equation has only 4 variables, you will be given 3 variables, and then you may apply an equation to find the 4th variable. The following examples showed how to apply the equation. In example 7, the initial velocity, acceleration, and time for acceleration are given. You have to find the velocity and displacement of a greyhound after its acceleration. In example 8, you are given 3 variables, namely displacement, initial and final velocities, and you have to find the acceleration. Try checkpoint 5 to see if you follow. In example 9, the principle of skid mark test is demonstrated. This is a very important example because it shows how to apply ratio to solve physics problems. You can quickly see that when the skid mark doubles in length, the velocity does not double. From the equation, you can see that the length of the skid mark is directly proportional to the square of initial speed. So when the skid mark doubles in length, the square of the initial speed doubles, and hence the speed increases by √2 times only. Example 10. Another important example. When a driver sees something ahead and he considers to brake, it takes a short time for him to react. This is his reaction time. During this time interval, the car has traveled a short distance called thinking distance. Then he finally applies the brake and the car still moves forwards during the deceleration. The distance traveled during the deceleration is called braking distance. Finally, the car stops. So the total stopping distance, or just stopping distance, is the sum of thinking distance and braking distance. Read example 10 carefully before you move on. You should note that the thinking distance is directly proportional to the initial speed, but the braking distance is directly proportional to the square of initial speed. Therefore, when the initial speed doubles, the thinking distance will double, but the braking distance increases by 4 times. If we look at the speed time graph, for a lower speed of v, then the speed time graph will go this way. The 2 areas represents the thinking distance and the braking distance. When the initial speed doubles, then the velocity time graph will go this way. The thinking distance doubles as the initial speed doubles. What about the braking distance? The braking distance increases by 4 times, as you can see, represented by the big green triangle under the black velocity time graph. And now read the STSC section at the bottom of the page. Three, equations of motion and motion graphs. The equation of motion can tell us the relationship between the motion parameters like displacement, initial and final velocities, acceleration, and time taken. So the equations may explain the shape of ST graph, VT graph, and even AT graph using the respective equations as shown in figure 2.2c and 2.2d. The equations of motion in some special cases produce special relationship to plot special graphs. For example, when the uniformly accelerated motion starts from rest so that u equals 0, then displacement s equals half at squared. A plot of s against t squared, as in figure 2.2e, will give a straight line graph of slope a/2. On the other hand, a uniformly accelerated motion will also give a v squared s graph of slope 2a, as shown in figure 2.2f. Read the exam link on the next page. This was a 2007 Hong Kong CE multiple choice question. In example 11, you are asked to describe how to use a light gauge to check if the trolley runs down the slope with constant acceleration. Now cover up the solution and listen to the following hints. You should apply the equations that you have learned in this chapter. You have to measure the speed v of the trolley when the trolley has traveled different displacement s. You have to plot a graph, which was mentioned on page 65. The acceleration is constant if the graph appears to be a straight line. Lastly, try checkpoint 6 on the next page.